Imagine a machine so precise, it forces reality itself to break character. We're not talking about black holes or the edges of the observable universe. We're talking about an instrument sitting in a laboratory in Colorado right now, measuring a dimension you take for granted every single second. But the numbers coming out of that lab are terrifying. They're proving that time, the very foundation of before and after, is fractured. Today's show is an inspiring celebration of impossible ideas and the minds brave enough to chase them down. Finding passengers bold enough to embark on our good ship's journey is harder than most people think, so drop a very humane thumbs up right now to send a signal flare to drifting knowledge pirates like yourself. We know they're out there, let's bring them home. We're keeping it lighthearted as usual, but we promise to never skimp on the intelligence. Now let's kick off this voyage with today's new revelations.
We really are looking at a fundamental crisis in physics here.
Yeah. So for everyone listening, our mission today on this deep dive is pretty ambitious.
Oh, absolutely.
We are looking at this incredible synthesis of independent research spanning multiple scientific disciplines. I've got this massive stack of sources here. Peer-reviewed papers, hard laboratory data, cosmological surveys, and, usually these fields don't talk to each other at all.
Right. They operate in almost total isolation.
Exactly. You have quantum physicists in one corner, cosmologists in another, and metrologists, the people who just measure things off in their own world entirely.
Yeah.
But when you lay all their current data out on one table, you see this terrifyingly cohesive picture.
And our goal for you today is to basically connect those dots that the broader scientific community is currently treating as, separate little anomalies.
Right.
We're going to track a series of these anomalies that are popping up everywhere, from microscopic quantum clouds all the way up to the expansion of the universe itself. And the singular paradigm-shifting conclusion we are just forced to reach is that our fundamental model of time is incomplete. The backdrop of reality isn't what we thought it was.
It's wild. And I want to start by looking at a very specific piece of hardware to ground this. This is happening at the National Institute of Standards and Technology, or NIST.
NIST, right, in Boulder, Colorado.
Yeah, in Colorado.
Yeah.
They have built an optical lattice atomic clock. Now, I used to think an atomic clock was just like a super accurate digital watch.
A lot of people do. It sounds like a consumer gadget.
Right. But the sources detail the actual mechanism here, and it's just mind-bending. They are trapping a single solitary aluminum ion in an electromagnetic field, just suspending one single atom in a vacuum.
And the isolation required for that is really the key. They have to strip away literally all environmental noise, heat, magnetic interference, vibrations from a truck driving by outside.
Wow, even a truck.
Oh, yeah, anything can disturb it.
Right, so they have this one atom trapped, and then they use lasers to probe it. They are measuring what's called an atomic transition. Basically, they hit this aluminum ion with a laser, and its electron jumps back and forth between two energy states.
That oscillation, that jumping back and forth, is the literal tick of the clock.
But the sources say aluminum is notoriously difficult to, read without destroying its state. So the researchers use this crazy technique called quantum logic spectroscopy.
Right, they bring in a helper atom.
Yeah, they pair the aluminum ion with a magnesium ion. They use the magnesium ion to essentially read the mind of the aluminum ion without disturbing it, applying the exact same logic gates used in quantum computing.
It's just sheer technical brilliance. And the result of that engineering is a measurement precise to 19 decimal places.
19 decimal places.
Right. Just to put that into context, this clock will not lose or gain a single second over 13.8 billion years.
Which is the entire age of the universe.
Exactly. It's the entire current age of the cosmos. But let's elevate this from just an engineering feat to a philosophical problem. At 19 decimal places, you aren't just measuring time anymore.
What do you mean?
You are building a probe into the physical fabric of reality. You are asking the universe, what exactly is happening right here at this exact coordinate in space? And what happens when you probe reality that deeply is that the fabric pushes back.
Right, and this is where gravitational time dilation stops being this theoretical whiteboard concept from Einstein and becomes a literal operational fact in a basement in Colorado.
Yeah, Einstein predicted back in 1915 that gravity isn't a pulling force, it's the curving of space-time by mass.
If you are closer to a massive object, you are sitting in more curved space-time.
Correct. And the deeper you are in that gravity, well, the slower time passes for you relative to someone further away.
But we always thought of this as like a black hole problem, right?
Yeah.
Like in that movie Interstellar, or something that only mattered over vast distances in space?
Well, we can measure it on a workbench now. The NIST team literally demonstrated this by separating two of these optical clocks by a vertical height of just 1 centimeter.
1 centimeter.
1 centimeter of difference in the Earth's gravitational pull. The clock that is 1 centimeter closer to the floor experiences a minutely stronger gravitational pull than the clock elevated just above it. And the clock on the bottom measurably ticks slower.
Okay, let's unpack this for a second, because understanding why gravity slows time is crucial here. Let's think about time less like a universal ticking metronome playing in the background of the universe.
Which is how most of us picture it, yeah.
Right. And let's think of it more like a river with different currents. If I'm standing in the deep water near the riverbed, which represents high gravity, the water is thick, the current drags, and my movements are slower. But if I'm floating on the surface in low gravity, I move faster. So the flow of reality is physically thicker the closer you get to mass.
I think a river with varying currents is a highly effective way to visualize this for everyone listening. General relativity treats space and time as a single woven fabric space-time. If mass warps that fabric, it stretches the physical distance between 2 points, sure, but it also stretches the duration between 2 moments. It is a purely local property. The rate at which you move through time is inextricably linked to your specific gravitational coordinates.
And the sources scale this up in a way that just completely shattered my perspective on the actual planet we live on.
Oh, the Earth's core.
Yes. If a 1 centimeter difference changes the flow of time, think about the Earth's core. It's roughly 6,000 kilometers deep, sitting under the immense gravitational pressure of the entire planet's mass.
It's in the deep end of the river.
Exactly. The surface, where we are, is in much weaker gravity. Because of that exact same physics, the river current dragging slower in the deed. The Earth's core has been aging slower than its crust for 4.5 billion years. The math literally shows the core of our planet is physically 2.5 years younger than the surface we're standing on right now.
It's the same planet. It was born at the exact same moment from the same accretion disk in the early solar system, yet it occupies 2 completely different temporal ages.
That's just wild.
And, this is actively dictating how we build our civilization today. It's not just fun planetary trivia.
Right. I was reading this 2024 White House memo in the sources about lunar infrastructure. We're establishing a permanent presence on the moon, and this memo formally directs the creation of coordinated lunar time.
Because of the gravity difference.
Yeah, because the moon has only 1/6 the gravity of Earth. The river of time flows faster on the lunar surface. So a clock on the moon ticks 58.7 microseconds faster every single day compared to an Earth clock.
Which sounds infinitesimal to you and me.
Right, a microsecond is nothing.
But modern communications, telemetry, and navigation require nanosecond precision. If you don't account for that 58.7 microsecond drift, over the course of just a few weeks, a lunar rover trying to land autonomously will calculate its position incorrectly by miles.
It would literally crash.
It will crash into a crater.
And we're already dealing with this exact thing on Earth. The global positioning system relies on a constellation of satellites sitting 20,000 kilometers up in space.
Way up in low gravity.
Right. Up there, gravity is incredibly weak compared to the surface, so their atomic clocks run about 45 microseconds faster per day. The GPS receiver in your phone calculates your location by timing how long it takes signals from multiple satellites to reach you.
It triangulates based on timestamps.
Exactly. If engineers didn't program Einstein's relativity equations into the software to artificially slow down the satellite clocks, the navigation on your phone would drift by 10 kilometers every single day.
So the entire modern digital economy rests on the mathematical acknowledgement that time is warped.
Okay, so we have this beautiful, validated operational model of time as a flexible, curving, dynamic dimension. But here's the massive fault line. This localized, flexible river of time from general relativity crashes directly into the other most successful, battle-tested theory of reality we have.
Quantum mechanics.
Right.
This is literally the intersection where physics breaks. General relativity handles the macroscopic universe, planets, stars, galaxies, gravity. Quantum mechanics handles the microscopic universe, the weird behavior of atoms, photons, and subatomic forces.
And they are both right.
Both frameworks are mathematically pristine in their own domains, but their descriptions of time are utterly, irreconcilably incompatible.
Let me make sure I'm translating the papers correctly here for the listeners. In relativity, as we just established, time is a physical thing. It bends. But in quantum mechanics, the math treats time completely differently.
Completely.
When you look at the Schrodinger equation, which is like the core math that describes how a quantum state changes time, is just a variable sitting outside the system. It's an independent, rigid, unbending background parameter.
It's just a ticking dial on the wall.
Yeah. You don't apply quantum rules to time itself.
That is the core contradiction. Quantum mechanics demands a fixed, immutable stage upon which particles can act out their probabilistic behaviors. It essentially says time is a neutral observer.
Right.
But general relativity says no, time is an active participant. It bends and warps based on the actors on the stage. You simply cannot mathematically merge a rigid parameter with a dynamic fabric.
But, I mean, I'm looking at my phone right now. The GPS uses general relativity, as we just said. But the microscopic semiconductor transistors inside the phone's processor operate entirely on the laws of quantum mechanics.
Yes.
The battery uses quantum chemistry. Both of these theories are visibly running the modern world simultaneously in my hand. Why can't theoretical physicists just force them together? What actually happens to the math when you try to blend them?
It's a disaster. When you try to combine the equations to describe, say, the gravitational field of an electron, the mathematics explodes into infinities.
Infinities, like the numbers just run away.
Exactly. The standard trick physicists use to handle infinities, a mathematical process called renormalization, it completely fails here.
Yeah.
Think about it. If gravity is a quantum field, then at the absolute smallest scales, gravity must be fluctuating wildly like all quantum fields do.
Okay, that makes sense.
But because gravity is space-time, that means time itself is fluctuating wildly. If time is constantly fluctuating in unpredictable ways, you can no longer define when an event happens.
Oh.
And if you don't know when an event happens, you can't calculate its probability. The equations just eat themselves.
So it's not just a bookkeeping error where we need like a slightly better calculator.
No, the foundations are totally mismatched, which forces us to ask, and this is where it gets really strange, what is actually happening to time at the absolute smallest scales?
Because the sources point to some experimental data on quantum collapse that suggests time might not even exist down there.
To understand the implications here, we have to look at the measurement problem in quantum mechanics. At the microscopic level, particles do not exist in a single definite state or location.
Right, they're fuzzy.
Exactly. A single photon or electron exists as a wave of probabilities, a superposition of all possible states. It is only when the particle interacts with its environment or is measured that this wave function collapses and it snaps into a single, definite, measurable reality.
And for decades, physicists have argued about what actually causes that collapse, right? Like, is a human observation, is the instrument. But the new theoretical work we are looking at leans heavily into an idea championed by Roger Penrose.
Yes, the Nobel laureate.
Yeah, that gravity itself is the trigger for quantum collapse.
The theory proposes that collapse is a physical mechanism driven by the curvature of space-time. Think about a physical object in a superposition of two different locations at once. Because mass curves space-time, an object in two locations is trying to curve space-time in two different ways simultaneously.
Which sounds impossible.
Well, the universe can tolerate this tiny blister of overlapping geometries for a single particle because a particle has almost no mass. The gravitational difference is practically negligible.
So a single atom can stay fuzzy in quantum for a long time.
But a massive object, say a bowling ball or a cat or a human, has massive gravitational weight. The spatial geometries of a bowling ball in two different places are vastly different.
It would tear space-time apart.
Exactly. The universe cannot sustain that severe contradiction in space-time curvature, so the system violently and instantly forces a collapse into one state. Gravity resolves the ambiguity.
Okay, I understand how that explains why we don't see floating, fuzzy, quantum bowling balls in our daily lives. But how does this gravity-triggered collapse mess with time?
Because if the geometry of space-time is what is doing the collapsing, then the collapse is subject to the fundamental limits of space-time. And there is a hard physical floor to reality called the Planck scale.
The Planck time. The sources define this as roughly 10 to the power of negative 43 seconds.
10 to the minus 43.
Yeah, I can't even offer a solid analogy for how small that is. It's a decimal point followed by 42 zeros and a 1.
At that unimaginably brief scale, the quantum fluctuations of gravity become so extreme that the smooth fabric of space-time actually dissolves. It turns into a chaotic, frothing mess, often called quantum foam.
Quantum foam.
Yes. Below the Planck time, the concepts of before and after lose all physical meaning. Duration literally ceases to exist. The act of a particle collapsing into reality and the geometry of time are so entangled at that threshold that you hit a hard wall. Time does not have a smooth, infinitely divisible flow.
And we are actually starting to see the cracks of this breakdown in real laboratory settings. I was reading this section of the source material about an experiment involving a Rubidium Cloud, and I honestly had to read it 3 times.
It's a very difficult concept to parse.
Yeah. So researchers fired a photon, a single particle of light, into a cloud of ultra-cold rubidium gas. They wanted to measure how long the photon spent interacting with rubidium atoms before it exited the other side.
A seemingly straightforward measurement of transit time.
Right. When a photon enters the gas, it interacts with the atoms. It gets absorbed and re-emitted, essentially tunneling through the medium. Now, the photon is a wave packet, a little bundle of probability. But the atomic resonances of the rubidium gas interact with the photon's wave in such an extreme way that they actually reshape the wave packet itself. And the lab results show that the peak of the photon's exiting wave emerged from the cloud before the peak of the entering wave had even fully entered.
The mathematics of the interaction yielded a negative group delay.
I want to make sure I'm translating this perfectly for you listening.
Yeah.
The photon spent a negative amount of time inside the material. It exited before it entered.
Which sounds like magic.
Right, and this isn't a glitch in the laser. It's not a rounding error on a spreadsheet. The math of quantum mechanics entirely permits this negative transit time, but it is completely alien to our everyday intuition of cause and effect.
And it forces a profound reevaluation of what time really is. If a particle can experience negative time, or if duration breaks down entirely at the Planck scale, it strongly suggests that time is not a fundamental building block of the universe.
Let me try out an analogy here to see if I am grasping this, because it's a lot. Let's think about time like we think about temperature. If you have a single helium atom floating in a perfect vacuum, it does not have a temperature. Temperature is not a property of a single particle. Temperature is the statistical result of billions of atoms bouncing around, colliding, and transferring kinetic energy. It only emerges when you have a crowd.
Right, it's a macroscopic phenomenon.
As I understanding correctly, the leading edge of physics is suggesting time itself is emergent in exactly the same way.
That is a remarkably accurate analogy, yes. Time may be an emergent property of macroscopic, many-particle systems. It is the statistical motion of the crowd.
Wow.
At our level, the level of human beings, planets, and coffee cups, the crowd is massive, so time feels solid, measurable, and very real.
Yeah.
But if you zoom into the foundational level of reality, to the single particle, the concept of time evaporates, just like the concept of temperature.
And if time is just an emergent property of the crowd, that gives us the perfect lens to examine the most infuriating obvious mystery of all, the arrow of time.
Yes.
Why does the crowd only ever move in one direction?
It is the ultimate paradox of physical law.
Right, think about the fundamental equations of physics. Newton's laws of motion, Maxwell's equations for electromagnetism, Einstein's relativity, even the Schrodinger equation in quantum mechanics we just talked about. In every single one of these bedrock mathematical frameworks, time is completely symmetric.
Yes. The math doesn't care.
You can run the variables forward or backward, and the math works perfectly. Nothing in the deep code of the universe cares whether time flows from past to future or future to past.
The physics is entirely indifferent.
But the reality we live in is brutally directional. A glass falls off the table and shatters into 100 pieces on the floor. It never ever unshatters and floats back up to form a perfect glass in your hand. We remember the past, but we don't remember the future. We get older, not younger. The arrow of time only flies one way.
The traditional textbook explanation for this asymmetry has always been entropy, which is rooted in the second law of thermodynamics.
Right, entropy.
Entropy is simply a measure of disorder. The second law states that in a closed system, disorder will always increase over time.
Because there are way more ways for a system to be messy than to be organized.
Precisely. If you drop a glass, there is only one specific arrangement of atoms that makes a perfect, intact glass. But there are trillions of different arrangements of atoms that constitute a shattered, broken glass on the floor.
It's just a numbers game.
It is simply a matter of probability. A system naturally evolves from a highly improbable state of order to a highly probable state of disorder. We experience this continuous statistical slide into messiness as the forward march of time.
But the sources highlight a massive conceptual trap in this textbook explanation.
They do.
The second law of thermodynamics is statistical. It is not a rigid fundamental law of physics like the conservation of energy. It's just a probability argument. It actually does not forbid the glass from unbreaking.
No, it doesn't.
It doesn't forbid heat from flowing out of your coffee cup and into the ice cube. It just says the odds of all those trillions of atoms perfectly coordinating to run in reverse are so astronomically low that you will outlive the universe before you see it happen.
It is a trick of scale. And this brings us to a groundbreaking piece of research from the University of Surrey that was highlighted in our material. They investigated the arrow of time by looking deeply at open quantum systems.
An open quantum system being one that isn't perfectly isolated in a vacuum, right? Like it interacts with its environment, exchanging energy and information, which basically describes everything in the real world.
Exactly. Nothing is truly closed off. They analyzed the complex mathematics governing how these messy interactive systems evolve. Our assumption has always been that once a quantum system interacts with a chaotic environment, the information of its original state is lost forever into the noise. The irreversible arrow of time just takes over.
Yeah.
But the researchers at Surrey found something hidden in the math. They identified what they call a memory kernel.
Okay, I'm going to need you to break down what a memory kernel is because it sounds like sci-fi.
A memory kernel is a mathematical property within the equations of the system's evolution. It acts as an underlying record. The mathematics revealed that even in these highly complex, open systems that appear completely irreversible to us, the microscopic reversibility is never actually destroyed.
Wait, really?
It is preserved mathematically within the structure of the system's interactions with its environment.
So it's like unstirring cream from coffee. When I pour cream into black coffee and stir it, it looks completely irreversible. The cream is gone. It's just brown coffee now.
Right.
But if I somehow had a supercomputer that could track the exact trajectory, momentum, and position of every single liquid molecule, the physics says I could perfectly reverse the exact kinetic energy of the spoon and separate the cream back out. The information isn't destroyed, it's just scrambled beyond my macroscopic ability to perceive it.
That is exactly what the memory kernel represents at the quantum level. The reversibility is there. The information of the past state is hidden, but mathematically intact.
So what does this actually mean for you, the listener? We are saying that the one-way flow of time is essentially an illusion created by our own blurry vision. We are big, warm, macroscopic biological machines. We can't perceive the microscopic reversible tracks, so we just experience the statistical blur of entropy and call it the flow of time.
The profound implication is that the arrow of time is not a hard feature of the universe. It is a large-scale approximation. At the foundational level, time has no preferred direction.
That is just wild.
The asymmetrical experience of reality, the fact that yesterday is locked away and tomorrow is unknown, is a phenomenon the universe produces only at large scales. It sits on top of a foundational physics that simply does not contain an arrow.
This breaks my brain a little bit, because if the past and the future are just approximations, and the timeline isn't physically rigid, what happens if we merge that quantum weirdness with the incredibly precise optical clocks we talked about in the beginning?
Ah, Schrodinger's clock.
Yes. I was reading the section in our sources on Schrodinger's clock, and it feels like the exact moment theory becomes a terrifying reality.
So we are all familiar with the famous thought experiment of Schrodinger's cat. A cat is placed in a steel box with a tiny vial of poison gas, a Geiger counter, and a radioactive atom.
If the atom decays, the counter triggers, the vial breaks, and the cat dies. If the atom does not decay, the cat lives.
But because radioactive decay is a quantum event, until you open the box and measure it, the atom is in a superposition of both decayed and not decayed.
Which means the entire system is entangled. Mathematically, until the box is opened, the cat is in a superposition of being simultaneously alive and dead.
Both states are physically co-present in the wave function. It highlights how the fuzzy probability of the microscopic world scales up to macroscopic objects.
But the physicists in these papers ask a devastating follow-up question. What about the clock inside the box? The clock that is recording the exact time the radioactive trigger fired.
This is where it gets heavy. If the event that decides the cat's fate exists in a superposition of possibilities, then the moment that event happened must also exist in a superposition. The timeline of the event is not fixed.
And researchers are moving this out of the realm of hypothetical cats and into actual experimental proposals using those optical lattice clocks.
Yes.
We already established that a clock ticks slower the closer it is to a gravitational mass. So what if you take an atomic clock, a system that can measure time to 19 decimal places, and you put its internal components into a quantum superposition of two different physical heights?
Which is technically feasible.
Yeah.
We can put particles into spatial superpositions. If the clock mechanism is simultaneously existing at height A and height B than it is experiencing two different gravitational pulls simultaneously.
Because it's literally in two places at once.
Correct. And because it is experiencing two different gravitational fields, the rate at which time passes for the clock is also in superposition. General relativity demands the clock tick slower at the lower height. Quantum mechanics demands the clock exist in both starts. The mathematics dictate that a single clock is measuring itself ticking at two different rates simultaneously. One unified physical system, two distinct timelines coexisting.
I need to pause here because this challenges the absolute deepest assumption I have about reality. I assume, and I think you listening assume, that the present moment is the only truly real thing. The past is a memory, the future is just potential, but now is singular and solid. But you are saying the math proves there could be multiple nows overlapping.
It fundamentally attacks the singular nature of reality. If a clock ticks at two rates simultaneously, the question, what time is it reading right now, does not have one answer. There is a superposition of readings, a superposition of physically real nows.
But we don't see that.
Right now, standard physics will interject here to remind us about decoherence.
Right, decoherence. This is the mechanism that stops us from seeing overlapping realities.
Yeah.
Explain how that works, because I think it's crucial for understanding why everything looks normal to us.
Decoherence is the process of a quantum system leaking information into its environment. Remember, quantum states are fragile. The moment a stray photon or a molecule of air bounces off that clock in superposition, the environment has effectively measured it.
It breaks the spell.
Yes, the mathematical wave function entangles with the environment, and the superposition rapidly decays into a single classical state. The overlapping nows collapse into one timeline.
The window of weirdness closes instantly.
Almost instantly in our hot, messy, macroscopic world. But the critical philosophical point is that the window opens at all. The underlying code of the universe physically permits multiple time states to exist simultaneously. The present moment is not singular at the foundation of reality.
That's haunting.
And what is truly unsettling is that this temporal instability isn't just a microscopic quirk. We are seeing evidence of it across the entire history of the universe.
Which is a perfect pivot to deep time. I want to jump from the microscopic scale all the way to the cosmic scale, starting with a paper published in 1937 by Paul Dirac.
One of the founding giants of quantum mechanics.
Yeah, and he looked at the fundamental constants of physics. Things like the speed of light, the gravitational constant, the mass of an electron, and the fine structure constant, which basically determines how strongly electromagnetic waves interact with charged particles.
These constants are the cheat codes of reality. They are the arbitrary numbers you plug into the equations to make the universe work. We don't know why they have the specific values they do, but if they were even slightly different, stars wouldn't ignite, chemistry wouldn't work, and the universe would be a dark void.
We call them constants because we assume they never ever change. But Dirac hypothesized that they might actually be evolving slowly over billions of years as the universe ages.
Yeah.
He suggested the rules of the game might be shifting.
It is a radical proposition, because if these numbers drift, the very mechanics of existence drift with them. The speed of light dictates the speed of causality. The fine structure constant dictates the energy levels of atoms.
And to test Dirac's theory, the sources point to an absolutely incredible location in Gabon, West Central Africa, called Oklo. I was fascinated by this. About 1.8 billion years ago, a uranium deposit there spontaneously achieved nuclear criticality.
It is the only known natural nuclear fission reactor on Earth.
I had to look up how this is even possible. 1.8 billion years ago, the natural concentration of uranium-235 in the Earth was about 3%, which is roughly the enrichment level used in modern power plants.
Right.
Groundwater seeped into the uranium ore. The water acted as a moderator, slowing down the neutrons just enough so they could split other uranium atoms, initiating a chain reaction. The reaction generated intense heat, which boiled the groundwater away. Without the water to slow the neutrons, the reaction stopped.
It moderated itself.
Exactly. The rock cooled, groundwater seeped back in, and the reactor started up again. It pulsed on and off like this for hundreds of thousands of years.
It is a geological miracle, but for physicists, it is the ultimate time capsule. Nuclear chain reactions are exquisitely sensitive to the fundamental constants, particularly the fine structure constant. When the Oklo reactor burned, it left behind specific ratios of fission products like isotopes of samarium and neodymium.
Okay.
The ability of samarium-149 to absorb a neutron is directly governed by the fine structure constant.
So physicists today dig up this 1.8 billion-year-old rock. run it through mass spectrometers, and measure the exact ratios of these isotopes. If the fine structure constant was different almost 2 billion years ago, the reactor would have produced a different ratio of samarium isotopes than a reactor would produce today.
And when researchers analyze the Oklo data, the ratios match our modern constants incredibly closely, which on the surface seems to debunk Dirac. It seems to prove the constants are rock solid.
Right, but
But as the papers emphasize, close is not identical. The Oklo data places a strict upper limit on how much the constant could have varied, proving any variation is incredibly tight. But it does not rule out variation entirely.
And when astronomers look even further back in time, billions of years into deep space, they see a different story. They analyze light from distant quasars. This light has traveled for 10 billion years, passing through ancient clouds of intergalactic gas on its way to Earth.
As the light passes through the gas, the atoms in the gas absorb specific wavelengths, leaving dark lines in the light spectrum. Because atomic absorption is dictated by the fine structure constant, analyzing these absorption lines allows us to measure the constant as it was 10 billion years ago.
And multiple observational studies have detected slight variations. We're talking about shifts in the 5th or 6th decimal place, and I know it's a topic of fierce debate in the astrophysics community, but the signal is there. The constant might actually be a variable.
Furthermore, advanced theoretical frameworks, particularly string theory, expect these constants to drift. In models with extra dimensions, what we perceive as fundamental constants in our 3D space are actually determined by the shape and size of the unseen extra dimensions. If those dimensions slowly expand or contract as the universe cools, the constants will drift with them.
Let me ground this for you listening, because the implication regarding time is massive. We just spent the first half of this deep dive establishing that our most precise clocks measure time by counting atomic transitions. Those atomic transitions are strictly governed by the fine structure constant.
Yes.
If the constant is drifting over billions of years, then the physical mechanism that defines what a second is drifting. The second you are experiencing right now listening to us speak is literally not governed by the exact same physical parameters as the second the dinosaurs experienced.
The ruler we use to measure time is warping. The physical reality that the concept of a second is anchored to is a moving target. And if the foundational rules governing time are evolving over the lifespan of the universe, it forces us to ask an even larger cosmological question.
Because
What is happening to the container of time itself?
which takes us to the absolute edge of cosmology and the cosmic inventory. When you zoom all the way out and look at the mass energy density of the entire universe, normal matter, which is every star, every galaxy, the Earth, you, me, the device you're listening on, makes up exactly 5% of the universe.
Just 5%.
Dark matter, the invisible scaffolding that holds galaxies together, makes up about 27%.
Yeah.
And a staggering 68% of the universe is comprised of dark energy.
Dark energy is the grand ghost of modern physics. It was discovered in 1998 when astronomers realized the universe wasn't just expanding, the expansion was accelerating. Something is overpowering gravity on a cosmic scale, violently pushing the fabric of space-time apart. We call it dark energy simply because we have no idea what it actually is.
We used to treat dark energy as a cosmological constant, like a stable, unchanging property of empty space. The idea was that as space expands, more space is created, meaning more dark energy is created, pushing at a constant rate.
Right.
But the papers dropped some explosive data released in 2024 from the DSI project, the Dark Energy Spectroscopic Instrument.
DTI is a massive undertaking. It mapped millions of galaxies to trace the history of the universe's expansion over 11 billion years. They do this by measuring baryon acoustic oscillations.
Which are what, exactly?
They are essentially fossilized sound waves from the plasma of the early universe that dictated where galaxies would eventually form. By mapping these structures at different distances, they can perfectly trace the expansion rate over deep time.
And what DCI found completely shatters the constant model. The data suggests dark energy is evolving. It only became the dominant force pushing the universe apart about 5 billion years ago. And its strength, its behavior, is changing dynamically.
It behaves more like a fluctuating field, sometimes referred to as quintessence, rather than the constant property of the vacuum.
And this is a big deal, right?
This is deeply terrifying to a physicist. General relativity established that space-time is a single integrated geometry. Time is woven into the spatial fabric. If the universe is expanding, the geometry of time is expanding. If the dark energy driving that expansion is mutating and changing its behavior over billions of years, then the large-scale geometry of time itself is mutating.
Wait, I really want to press you on this to make sure I'm visualizing this correctly. Are we saying that a billion years of duration measured today in our current epoch of the universe is not the same as a billion years measured back when the universe was half its size? The actual physical container of time is morphing while we are living inside it.
That is the profound, unsettling reality. The expansion rate was different, the spatial geometry was tighter. Time passed through a differently shaped cosmic environment. We mentally treat units of time like empty glass jars. A billion years is a jar of a certain size no matter where you put it.
Right, a billion years is a billion years.
But at cosmological scales, the glass jar itself is changing shape and volume. 95% of our universe is made of components we cannot identify, dark matter and dark energy, and the 68% that is driving the macro structure of time is actively evolving in ways our models failed to predict.
All of this brings me to a massive, glaring question about how science is communicating this. We have discussed a localized time that bends over a single centimeter. We have quantum physics showing particles experiencing negative time and an arrow of time that might just be a statistical illusion.
Yes.
We have constants that might be drifting, and a mutating dark energy warping the cosmic timeline. If our foundational understanding of reality is this fractured, why isn't this the front page headline of every newspaper? Why aren't scientists shouting from the rooftops?
Well, it comes down to the sociology of institutional science. We can look at a perfect example happening right now, the international effort to redefine the second.
Right, the current definition of a second, established in 1967, is based on the cesium microwave clock.
Yeah.
It is exactly 9,192,631,770 oscillations of a cesium atom. But as we discussed at the start of the show, the new optical lattice clocks using aluminum or strontium are vastly superior. They are 41% more precise, hitting that 19 decimal place mark. The old 1967 definition is literally too crude to describe the precision of the new instruments.
So the International Bureaus of Weights and Measures are preparing to officially update the definition of the second by 2030. But the irony here is palpable. These hyper-precise optical clocks have outgrown their original purpose.
How so?
They are no longer just keeping time. They have become incredibly sensitive gravity sensors. They are literally capable of watching the fundamental constants drift in real time.
The machines we built to measure the theory have outpaced the theory itself. They are sensing a reality that our current mathematics cannot unify.
And yet, the scientific silence on the macro implications is deafening. The reason is that the professional logic of academia rewards narrow, specialized mastery. Career incentives demand extreme caution. A metrologist building a better clock is not professionally incentivized to call a cosmologist studying the DSI dark energy data to debate the illusion of the arrow of time.
That makes sense, unfortunately.
Making broad, paradigm-shifting claims is where funding gets cut and careers stall. Publishing highly specific, precise, narrow findings is how you secure tenure.
It feels like we have built a microscope so breathtakingly powerful that we can see the lens of reality itself is cracked. But instead of physicists stepping back and asking, why is the glass fundamentally broken? They are just meticulously recording the exact coordinates of the cracks.
They're missing the forest for the trees.
The real story here is the convergence of all these fields. Time is local, it is quantum, it is emergent, it is statistical, and it is evolving. But institutional science is treating this absolute convergence of reality-breaking anomalies as a simple engineering and metrology problem to just calibrate a better clock.
The technological capability of our instruments has penetrated a layer of reality that our underlying vocabulary simply cannot describe yet. We are treating a foundational crisis in physics as a calibration issue.
So, to synthesize this entire journey for you listening, we started in a basement in Colorado, where a 19 decimal place optical clock proved that the river of time flows differently across a vertical height of just 1 centimeter, warping the age of the Earth's core. We dove down into the subatomic quantum realm, where gravity might be triggering collapse, where particles mathematically experience negative transit time, and where the irreversible arrow of time appears to be just a statistical illusion covering up a reversible universe. We stared into the paradox of Schrodinger's clock, confronting a reality that fundamentally permits multiple overlapping nows. We zoomed out to the deep time of the Oklo nuclear reactor, realizing the fundamental cheat codes of the universe are drifting. And finally, we look out to the edge of the cosmos, where mutating dark energy is warping the very container of space-time we exist inside. The fundamental backdrop of reality isn't a backdrop at all. It is dynamic, local, emergent, and beautifully incomplete.
If we connect all of this to the bigger picture, it raises an incredibly important question. We have spent this entire deep dive looking at time through external instruments, atomic clocks, quantum sensors, mass spectrometers, telescopes. But what about the instrument of the human mind? If the one-way arrow of time is just a statistical illusion at the large scale, and if the singular present moment is fundamentally unmoored at the quantum level, is human memory, and our linear perception of a flowing timeline just a biological coping mechanism? Is our consciousness simply a localized evolutionary tool designed to help our brains survive an underlying reality where the past, present, and future are actually suspended together in an infinite superposition? Think about that the next time you check your watch.
The outro music is by Rainbow, our resident 6 Android girl band from near-future Bavet, Cambodia. They are the undisputed baddest band in the universe, and today's song is called Chrome. All finished songs are performed live using the Abacus platform by the band's creator, Human Performance in the Age of AI, reclaiming your humanity from the algorithm. Be sure to share the playlist with someone who has the mental bandwidth to absorb these provocative ideas. Links are in the description below. Enjoy the music. Thanks for tuning in.
I see myself in polished steel. Something new begins to feel. Looking back at who I am, touch the surface with my hand. Orange light